And so today we've got alternating series and the ratio test. So an alternating series is simply of the form some sort of minus 1 to the n times another sequence. Or, of course, so sometimes the other things you will see, the book likes to do an n minus 1. I like to use an n plus 1 whenever we're shifting the index of where we start the negatives. For a strictly positive sequence. So in some sense, it's like anytime you see a sequence that's just alternating pluses and minuses, that's an alternating series. This is like a mathematical formalism to kind of describe that phenomenon. So for example, in this first one, when n starts at 1, we will have minus b1 plus b2 minus b3 plus b4. And of course, in this one, because when n starts at 1, my exponent for the minus 1 is going to be 0. So that means the first term is going to start positive for this one. So here we'll have a positive b1 minus b2 plus b3 minus b4. And since all the original b's were positive, their sign is really dictated by the sign that's out front of them. So the the odd terms are negative in this case. Here it's the even terms that are negative. So our tests for convergence, the nice thing about alternating series is they almost always converge. As long as they pass, namely the divergence test. So if we have a series, minus 1 to the n times bn is a series with, so all the individual terms, all the bn's are positive, namely it matches what we were just saying, that the sign in front of the bn is only dictated by the minus 1 to the n, and it's decreasing. So as long as it's a monotonically decreasing sequence whose terms are alternating, then the series converges. That's all there is to it. You really just have to ignore the minus signs, see if the terms are going to 0. Oh, I didn't write that term. So let me write out one extra condition. And we have to pass the divergence test. So we need a decreasing series. Of course, the terms have to go to 0. And then it'll converge if it's an alternating series. So for example, if we take our harmonic series, that's a divergent series. But if it's alternating, then, right, what is this equal to? If we wanted to sort of put it in the format that was previously there, we could have it as a pull out one factor of minus 1. Then it's minus 1 to the n times 1 over n. And so, of course, here, our bn is 1 over n. And what does 1 over n satisfy? They're all positive, and it's decreasing, right? I know that's 1 over n plus 1 is always going to be less than 1 over n. And of course, we know that the limit of 1 over n goes to 0 and going to infinity. And of course, we have an alternating series. And so I'm going to abbreviate alternating series test, this converges.
I do have a question.
Yeah.
So for the 1 over n plus 1 is less than 1 over n, and it's always true, but wouldn't it, since you're alternating, wouldn't one always be negative? Wouldn't that be true only half the time?
Well, so that's the whole point, is we're kind of factoring out that negative part. The decreasing part is only on the non-alternating. So, right, our Bn is just 1 over n. We're considering the series as a product of two things. One is the alternating, the minus 1 to the n, which creates the alternating, times some other series. Does that make sense? And it's only the conditions on this other series. So we kind of just ignore the alternating, ignore the plus or minus at first.
Okay.
And then only consider what's going on with the series without the plus or minus. Is it decreasing and does it go to 0? Then if it is alternating, once we add back in the alternating, it'll convert.
Yeah, we're just making sure it's decreasing for that test then. That's all we're doing.
Yeah,
okay.
Exactly. So essentially the only thing, if it's an alternating series, that you got to be careful about is really, are one of those terms violated? We're either not decreasing or the terms don't go to 0. Oops. Sorry, that should be 3n over 4n minus 1. Sorry, I'm off the page or off the video. So problem statement would be something like, determine whether this series converges or diverges. We have an alternating series, but what's happening to the terms? So we ignore the plus or minus, or the minus 1 to the n, and the other terms, as n goes to infinity, 3/4. So it's not 0. And so really this is just diverges by the divergence test. And that's basically all there really is to it for the alternating series test. So one thing we have is sort of built on this is absolute convergence. And so if we look at a series like, let's say, minus 1 to the n minus 1 over n squared, again, my individual terms, if I ignore the minus 1 to the n, or in this case, the minus 1 to the n minus 1, it's just going to be 1 over n squared. And so those terms are decreasing monotonically, and of course, the limit goes to 0. So this one will converge by the alternating series test. But it's also a little bit stronger. We want to check absolute convergence. So what is absolute convergence? It just means we take the absolute value of the terms And what do we get when we take an absolute value? Well, anything that's positive is going to stay positive. Anything that's negative is going to become positive. So the absolute series is just 1 over n squared, which we know by the p-test still converges. And so we say that the series minus 1 to the n minus 1 over n squared converges absolutely. So any series that converges absolutely will converge without the absolute values. So absolute convergence implies convergence. So this will be somewhat useful in these alternating series. It's more useful in the ratio test, which is coming up. But then occasionally you get these sequences that aren't quite alternating, that are just kind of funky with some sort of like trig functions, namely sine or cosine. So for example, let's suppose we want to determine the convergence of a sequence that is given by cosine of n over n squared. Well, cosine of n, what's that going to look like? It's going to look like a bunch of crazy decimals. It's going to be, I don't know. I mean, you would have to plug in integer values into cosine, and of course, it's measured in radians. And so you're going to get a bunch of crazy decimals. Some are going to be positive, some are going to be negative. And so essentially what you can do with this one is we can check the absolute value. And we would just get absolute value of cosine of n over n squared, which I know is now always positive because we're taking the absolute value. And I can now bound it by a comparison test with just 1 over n squared, since cosine, absolute value of cosine, is always going to be less than 1. And so by a comparison test, I know that the absolute value of the sequence or the series converges. So the regular series has to converge. So since it converges absolutely, in other words, the absolute value of the terms converges, then the general series will also converge. Any questions on any of that? So I guess the last thing to note on those guys is any sequence that we consider. So let's consider one more example. Convergence. Determine the convergence of -1, let's say to the n+1 over n. And actually, let me see. I think I had a different example here. Let's write this as n cubed plus 1 and have an n squared on top. So we want to determine when and how and if this converges. So one thing we can note is that in absolute value, we just have n squared over n cubed plus 1. Right, so taking the absolute value of this guy, my n's are starting at positive, so these guys are always positive, but it's that -1 to the n, which is essentially going to be dropped out when we take the absolute value. And what's going to go on with this guy? Converge or diverge? So what does this guy look like? It's a polynomial. This is our limit comparison, or even we could try a direct comparison. It seemed like most of you guys were starting to take to this limit comparison test, and we're liking that pretty well. And as I mentioned at the end of last class, anytime a comparison test will work, a limit comparison test will work. So if you don't even want to do comparison tests, you can always skip those and go straight to limit comparison tests, because those will always work in place of a comparison test, and they will work even beyond that when a comparison test won't work in certain situations. So if we compare the highest powers, n squared over n cubed, this should be like 1 over n. So if we compare it, let's take our limits of our original sequence divided by what we want to compare to. Compute that limit real quick. We'll have n squared over n cubed plus 1 times n over 1. We got to compute our limit. Of course, now I'll have an n cubed in the numerator, n cubed in the denominator. And so our limit is going to go to the ratio of the coefficients, which is just 1. So by limit comparison, we know that this sequence, n squared over n cubed plus 1, diverges since 1 over n diverges. So the series does not converge absolutely. But, well, now let's actually pay attention to the alternating series test. So one thing we do know is that the limit of the individual terms ignoring the alternating test, they still go to 0, so it passes the divergence test. And now what we need to check is decreasing. So they pass the divergence test. We check decreasing on the individual terms. Well, this one's going to be a little hard. Our n squared over n cubed plus 1, if we want to check it directly, similar to our previous one, at least with just 1 over n, we're pretty comfortable with saying 1 over n plus 1 is less than 1 over n. So I check the next term compared to the current term. Easy to see that comparison just with sort of a discrete math reasoning. In this case, if I consider an n plus 1 in here, I'll have an n plus 1 squared, n plus 1 cubed, then I'll have to compare it with this term itself. It's going to be a little trickier to make the same conclusion. So how do we show decreasing if we can't do it just kind of by a straight up discrete argument? We got to use some sort of calculus, some functions. So consider our f of x is x squared over x cubed plus 1 for x bigger than 1. How do I show decreasing? Well, we got to do a derivative. So f prime of x is going to be bottom, derivative of the top, minus the top, derivative of the bottom, all over the bottom, squared. Keep the bottom squared. It's nice when things are factored. Let's just do the algebra in the numerator. We'll have 2x to the 4th plus 2x minus 3x to the 4th. And so what are we going to get? We're going to get minus x to the 4th plus 2x over x plus 1 squared, x cubed plus 1, excuse me. The nice thing about the denominator, and anytime you have to do a quotient rule, it's always positive. So let's consider our range. Our range is from 1 to infinity. What are the zeros of the numerator? So it looks like actually if I plug in 1, it's actually going to be positive. If I plug in 2, however, so this will be negative for x bigger than 2. Everyone with me on that, or do you want to see me spell that out a little bit better? There's a little
Probably going to need you to spell that out.
Yeah, I think I went through that. Things happen in my brain because I do math all the time. So let's see what's going on there. How would we do this with calculus? Appropriate calculus steps. So we took our derivative. We want to set it equal to 0. When is a ratio equal to 0? Means we're looking for zeros of the numerator. So we factor out an x, and then we get, let's just factor out a minus x. We'll get x cubed minus 2. And so we get x equals 0 and x equals cube root of 2. So on our number line test, this is a little funky of what's going on. We've got 0, but we don't care about 0 because our original domain was 1 to infinity. And then we have, let's give some space. So here is cube root of 2, and it's going to cause a little bit of problems for us because cube root of 2 is slightly bigger. So I'll just put it as a smaller mark as 1. Yeah. And that 1 is kind of a problem because that's our first index. So this region we don't care about, certainly. We don't quite care about what's going on between 0 and 1, but by our calculus rules, everything that's happening between 0 and cube root of 2 it's either going to be strictly increasing or strictly decreasing. So how do we check that? We plug in a number. Let's say we plug in 1 into our first derivative. And if I check x equals 1, what do we get? Well, we'll get minus 1 plus 2 over... I'm running out of space on this page. Over 2 squared, which is negative. Positive, excuse me. Whereas if we check x equals 2, right, we'll get negative 16 plus 4 over something positive. So in the numerator, we'll have something negative. Denominator will be positive. Negative divided by a positive gives me overall a negative. Is that a little bit better? So what did we describe of this function using our Calc 1 tools? Our function is actually increasing from 0 to cube root of 2. Our function is then decreasing from cube root of 2 to infinity. So let's take a look. Let's write that out. So what did we have? We had x squared over x cubed plus 1. And our number line cube root of 2. We had a negative here and we had a positive here. And the problem is we had 1 somewhere in there. So f of x increasing 0 to cube root of 2. And it's decreasing cube root of 2 to infinity. And that's a little bit of a problem. Because, well, our 1 is over here, and from 1 to 2, so let's kind of put our indexes. So we have to compare our function with now a discrete function. The discrete function we care about when n equals 1, n equals 2. And unfortunately, because cube root of 2 is here, I know I was increasing up to that point, and then we're decreasing for all the terms after that. So what can we conclude? It's an alternating series. The terms go to 0. Does it converge or diverge? We have how many problem points? So let's actually be careful. Let's write this out. So we're considering this series, negative 1 to the n, and it was n plus 1. We had that shifted over n squared, n cubed plus 1. We're considering this guy. Even though we are not decreasing necessarily always, I can leave off the first term. What happens when n equals 1? I will have minus 1 squared times 1 squared over 1 cubed plus 1. So I'm just writing it all that just so it's clear that we plugged in 1 for n. And then we have minus 1 to the n plus 1. The same series. except now from 2 to infinity. And so now this guy will converge. Since the individual terms go to 0 and Bn is decreasing on 2 to infinity. So right after 2, that first index between 1 and 2 was a little weird because we were kind of increasing and then decreasing, and we couldn't really tell what's what. But it doesn't quite matter because I can always leave off the first term and say, well, from the second term and beyond, it's always decreasing. So by the alternating series test, it will have to converge. And since this guy converges plus a finite number, what even is that number? Is it just, so on the top we've got 1, on the denominator we've got 2? It's 1/2. So the whole series converges. Does that make sense? So we wanted to use the alternating series there. Little bit of a snag. This won't happen often. I think most of the time using the alternating series test, you won't have to do anything fancy with these indices. But just to kind of illustrate the process, usually the key thing is doing your calculus, checking that it's decreasing. In this case, we kind of ran into a little bit of a problem with the index, which hopefully won't come up very often. But in general, if it's decreasing for some interval out to infinity, it will converge. So our last note, we say that the series converges conditionally. But not absolutely. So anytime it asks, or if you see the word conditionally convergent, that means it's an alternating series, and it converges when it's alternating, but it won't converge if I apply an absolute value. Any questions on that guy? Okay, so let's talk about the ratio test. The ratio test is a rather strong test, but it doesn't quite work all the time. When it works, it's great because it's essentially saying that your series is eventually bounded by a geometric series, or at least comparable to a geometric series. So we're given some series. And this could be alternating. There could be a -1 to the n built into there, or it could be a fancy one with cosines or something that will make some of the terms positive, some of the terms negative, but in kind of a random way almost. So some general series, we want to compute the ratio of consecutive terms. Namely, we want to compute the limit as n goes to infinity of the next term relative to the current term. So an plus 1 divided by an. And we're actually going to compute this ratio, or the limit of this ratio, in absolute value. So let's say that we compute it and we get something. Could be infinity. Well, let's call it L. Here's our rule. So if L, so it's always positive. Actually, 0 is fine. If it's less than 1, the series converges. If it's bigger than 1, the series diverges. If it's equal to 1, the test is inconclusive. So let's see some examples. Well, suppose we want to know minus 1 to the n cubed over 3 to the n. So the first thing you should see with this is that it is alternating. We could try to do an alternating series test. What do we need to show? We would need to show that these terms go to 0, and we would also need to show decreasing. And as we just kind of saw in that previous example, hopefully you can see that the terms will go to 0 because we have an exponential on the bottom. Is it purely decreasing? Might be a little work to show that. Hopefully we could model this by a function, do a derivative, show that it's decreasing, show that it's always negative, and then you could apply the alternating series test. If you want to skip the alternating series test and go straight to a ratio test, there's some trade-offs, because if we try the ratio test and we get a limit as 1, well, then we can't conclude anything. Conversely, though, if we get something that's not 1, we can immediately conclude that it will converge or diverge. So let's go ahead and try this with our ratio test. We consider the next term. So we put in n plus 1s for everything, for all of your n's. We divide it by whatever the series says, the current term. And we are taking absolute values, so those minus 1 to the n's are going to go away. And we want to compute this limit. So let's do the algebra on this. Because we're taking absolute values, minus 1 to the n's, minus 1 to the n plus 1, those are going to go away. It's just going to make everything positive. So we are considering the limit as n goes to infinity now of, we've got n plus 1 cubed over 3n plus 1 times the reciprocal of the denominator, 3n over n cubed. Because the only terms being negative were these minus 1 to the n's. Once we get rid of those, all the remaining terms are always going to be positive, so I don't need the absolute values anymore. And so now what do we have? Well, we've got n plus 1 cubed over n cubed. And then 3 to the n divided by 3 to the n plus 1 can actually simplify to 1/3. And I didn't leave space right in my limit, so let's just draw the arrow and say as n goes to infinity, this sequence, what's going to happen? We've got n cubed over n cubed, and the coefficients are just 1. So this is going to go to 1 times 1/3, or just 1/3. So by the ratio test, since the value we got, 1/3, it's less than 1, the series converges. Sorry, did I take that away too fast? Was anyone still writing?
Thank you, I was.
Yeah. So one of the things that the ratio kind of helps us with, I mean, that we haven't been able to use something for so far is factorials. And some of these higher order functions, it's like n to the n and n factorial, where those functions, they're, beyond geometric series. And the algebra with them, as we've seen, can be a little tricky.
All right, I'm good.
So let's do one more example of this, and then I want to try to get you guys started on some of these homework problems, just because the homework, it looks like it could be a little long. Some of it might involve this ratio test, since you know it now. I don't know if you necessarily need it for some of the homework problems, but if you have a tool in your arsenal and you want to get used to practicing it and using it, not a bad thing to try on some of these problems. And just like with integrals, these series, it's kind of like a grab bag of tricks, right? With integrals, we had USUB, integration by parts, all of our different techniques for integrating. And you kind of have to just be able to recognize what's in the integral and know what tests, know what tricks to use to integrate it. It's kind of similar with these series. Now you kind of have a grab bag of tests, and you kind of got to get used to just practicing seeing a lot of series and trying to understand which test will probably be the best for it. So let's do an example. This example I'm going to say is going to be probably a good one to study. Actually, question to you guys. Do you guys want a ratio test question on the quiz? So ratio test will be on the midterm. It's hard to give it on the quiz since the quiz will be tomorrow without having you guys practice it. I could put like 1, but make it like 1 point, or maybe try to make it a bonus, though I don't know. I don't want to give too many bonuses, especially since I'm giving you another chance at last week's first one. I just want to make sure you guys are practicing it before the midterm. So something like this might appear. And let's see how to work with this, because we've got not just an n factorial, a 3n factorial, quantity 3n. And we've got some fancy stuff going on in the numerator. It's not an alternating series. There's no -1 to the n, which means all the terms are positive. We should check the divergence test. Do the terms even go to 0? Hopefully from previous discussions, as we've started in on these factorials, you should should kind of remember how factorials will grow a lot faster than exponential functions. So 5 to the n grows fast, but n factorial, let alone 3n factorial, is going to grow much faster. So I'll leave that to you guys to try to check, to remember how to check if that goes to 0. In any case, if you skip the divergence test and you do the ratio test, a correct conclusion on the ratio test, as long as your ratios are less than 1, it will converge. It will automatically imply that the terms go to 0. So let's check. We want to compute the limit as n goes to infinity of the next term divided by the current term. So we'll have an n plus 1 squared, 5 to the n plus 1 over 3 n plus 1, that whole thing factorial, divided by the current term, so just as it's written. I didn't put absolute values because it's not alternating. All the terms are already positive. So no need for absolute values there since we get the same thing. If you do put absolute values and then just get rid of them in the next step, fine. Not bad work. And so now let's just practice simplifying these guys. So we've got n going to infinity. We've got our n plus 1 squared, 5 to the n plus 1 over 3. Let's write it as 3n plus 3 factorial times the reciprocal of the denominator. We've got a 3n factorial then in the numerator, and then n squared times 5 to the n. My tips with these guys, I would say group similar types of functions. So like the polynomials, let's write as a polynomial divided by itself. So I'm going to put my n plus 1 squared over n squared. Let's put the exponentials on top of each other. So 5 to the n plus 1 divided by 5n, and then put the factorials on top of each other. It helps the algebra, but this guy simplifies pretty nicely. We can go ahead and keep our n plus 1 squared over n. So the nice thing, because all these functions, the different types of functions, you know, they really interact with the same type of function nicely. These ones, we know that the limit is going to go to the ratio of the coefficients because they're the same degree. So that limit's just going to be 1. Nothing much to do with that guy. This guy simplifies nicely. I will have a 5 in the numerator. And then what's going on with this guy? Factorials are the tricky ones. Always start with the biggest one and work your way down. So this is 3n plus 3, 3n plus 2 times 3n plus 1. And then what's coming next on the denominator? It would be 3n times 3n minus 1 times 3n minus 2. In other words, just another 3n factorial. So try to get used to factoring factorials. And so I just factored out these first 3 terms. And then the rest of the terms are 3n, 3n minus 1, 3n minus 2, which would be exactly the same as the numerator. And so how is that going to simplify? What are we left with? We're left with the limit as n goes to infinity, again, over n plus 1 squared over n squared times 5 times 1 over 3n plus 3, 3n plus 2, 3n plus 1. And now as n goes to infinity, we'll have 1 times 5 times 0. So by the ratio test, 0 is less than 1, so the series converges. Any questions? Anyone still writing? So this is the ratio test. Works nicely with these factorials and exponentials, as we've seen. It doesn't work very nicely if I'm just given a polynomial. Polynomials, if we're just given polynomials, p-test is probably better, because what would happen if I didn't have this extra stuff, these factorials and exponentials? If I were just given polynomials, the limit from a ratio test is just going to give me 1. So just to check that real quick, if I have the series of 1 over n squared, I know it converges by the p-test. But if we check the ratio test, we will have so when I flip the denominator, it'll be n squared over n plus 1 squared, and that's going to go to 1. So a 1, well, that's a 1 on the ratio test is inconclusive. Why is it inconclusive? Well, in this case, it converges by the p-test. But if I tried the ratio test with the harmonic series, just 1 over n, we're going to get 1 over n plus 1 divided by 1 over n. And that, again, just goes to 1. So a 1 by the ratio test, it could mean converge or it could mean diverge. We can't tell. The ratio test really doesn't work well with polynomials. It works great with exponential functions or functions that grow faster than exponentials, factorials, or even things like n to the n. Anyone still writing? Okay. All right, so we got about 20 minutes. Let's get you guys started on some of these homework problems. Let's see. So I've got numbers 2, 3, 5, and 13 picked out from homework 7. Number 5 is kind of one of the trickiest. This gets into what we call the interval of convergence. It's a ratio test one. Or no, it looks like, actually no, shouldn't be too bad. It's similar to one that you guys did on WebAssign recently. It's one where it says find values of x for which the series converges. You can do a ratio test for it. So maybe we'll do that one tomorrow. We could probably start off with that one tomorrow before we get going on the project. Let's take a look at some of these other ones. So number 2. We've got cosine of 5 to the k. This one's a little tricky because it's not cosine of 5k. Remember, it's compute whatever cosine of 5 is and then raise that to the k. Well, we need to make a little bit of an argument here. What is cosine of 5? We're not supposed to be using calculators, though I guess on homeworks there are certain calculator problems. We want to make a claim. Cosine of 5, is it less than, greater than, in absolute value, is it less than 1 or bigger than 1? We know that cosine x equals 1 has solutions of 2 pi, integer values, integer multiples of 2 pi. And I know that, well, 2 pi is about 6.28. So since 5 is not equal to 2 pi n for any n, we know that cosine of 5, at least in absolute value, has to be less than 1. Could be negative, but the whole point is cosine and sine, their range is between -1 and 1. 5 is a funky number because it doesn't work nicely with the unit circle, but we can at least argue that cosine of 5, whatever 5 radians is going to be some fraction less than 1. And so by the geometric series test, this converges. If we need to find the value, k equals 1 to infinity. So we're starting at 1, which means we're going to use it r over 1 minus r formula. And our r in this case is cosine of 5. And that's all we leave it as. If we don't use calculators, we can't compute cosine of 5. Cosine of 5 is just cosine of 5. And I know the denominator's not 0 because cosine of 5 wasn't 1. Let's take a look at number 3. So now we want, so same, I think, directions, determine whether it converges or diverges. And I think if it converges, we want to actually find the value it converges to. So natural log of k over k plus 1. This one's a little weird. Does it pass the divergence test? One thing we always want to check, right? Especially if it looks a little funky and we're not recognized If we don't recognize it as a sequence that decreases rapidly and don't recognize it as a sequence that goes to 0, never hurts to check. Does it actually go to 0? So what happens when I compute the limit? Well, as k goes to infinity, it'll go to natural log of 1, which is 0. So that's good. Passes the divergence test. It's not alternating. It's not geometric. So what can we do for this guy? So this is kind of going through our list of grab bags. Divergence test, check. But the divergence test doesn't tell us much more, right? Could still diverge, could still converge. All I know is it at least pass our initial pass through. It's not a geometric series, so that's kind of rules out any of those tests. It's not an alternating series, so that rules out any of those tests. So what do we have left? We have the ratio test now. We could try that. It might be a little tricky with the ratio test. The other thing we could try, anyone see? Anyone see the thing? The other thing?
Break up ln into lnk minus lnk plus 1.
Yeah, exactly. Natural logs are these functions. They don't appear very often in series and sums, but if they do and you see ratios or products, remember your properties of natural logs. And now anytime you see something like this where it's like natural log of k minus natural log of k plus 1, or any term that's like 1 over k minus 1 over k plus 1, is saying take the natural log of your current term minus the natural log of the next term. And if we're subtracting off something, the same functional value of the next term, this is in a telescoping series. So you would just want to write it out that it's going to be natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4. And it's going to keep going. And through the magic of infinity, since we keep going out and out, every term is going to end up adding with its negative, except the first term. And so the whole series, the sum of the whole series is actually just 0.
I had a question about that.
Yeah.
Wouldn't the last term, I had it when I was doing this, the last term, it would be ln k plus 1 with the ln of 1. Is that, so that's wrong?
What do you mean? So your last term out here?
Yeah, my last term out there I kept.
Yeah, so it would be a k plus 1, but because we're going all the way out to infinity, that k is going to keep getting bigger and bigger and go out to infinity. And the terms, in some sense, what's really going on here is that natural log grows so slowly that the terms are so close to each other. The consecutive terms, the positive negatives are so close to each other that they essentially all cancel out. That the net remainder after I add up all those terms together is 0. Any other questions? Let's see. I think we got one more. Actually, hang on. I'm thinking about that one for a second. It's a little weird. One of the problems with this telescoping series is that if I write it as a telescoping series, that these individual terms just go to infinity. And of course, it'll be infinity minus infinity. So it is a little weird that I have bigger and bigger terms. And if we were to write out the individual terms, it'd be natural log of 1/2 minus plus natural log of 2/3 plus 3/4 natural log. And all of those terms are negative in a weird way, but they should still cancel out and ultimately get 0, it looks like. Okay, so let's do one more. I think this is number 13. We've got the sum of k e to the minus 2k. K equals 1 to infinity. So we went through our list of checks. And hopefully everyone kind of sees that as it goes to infinity, even though k is going to infinity, e to the minus 2k is going to 0. And this e to the minus 2k is going to be much more dominant. And if you want to write it as k over e to the 2k, you can do a L'Hopital's rule to check. The terms will, in fact, go to 0. So it passes the divergence test. How do I find out if this converges or not? The things you want to look for now. So it's not alternating. Don't need an alternating series. Is it geometric? Not quite, right? It's kind of geometric. We have a geometric function going on. This e to the minus 2k is a geometric function. It's an exponential function. The problem is it's not just purely an exponential function. With our geometric series, we wanted to find our ratios, right? The first step was to manipulate the terms, modify them around till I get it as something to the n or something to the k. We can't quite do that here. Here we could write it as like an e squared to the k, but this is not an exponential term. It's a polynomial. It's just k to the 1. So we've got this combination of a polynomial and an exponential. And because we have a product of the two, we can't use a purely geometric series test. So no geometric series, no alternating series. These are the types of cases where we want to do ratio tests. So combinations of polynomials and geometric series, ratio test works great. Any combination of polynomials or anything higher in terms of rate of growth than a polynomial. So if you're combining exponentials, factorials, or even n to the n, any of those combined together, combined with polynomials, work great with using the ratio test. And essentially what the ratio test will show us is that even though this isn't a purely geometric series, compared to the geometric to the exponential part, this polynomial part isn't gonna make a difference. It's not gonna matter. That the exponential part will sort of dominate it in such a way. It'll be decreasing so fast that it will still behave very similar to a geometric series, at least in how it's going to converge. So let's check our ratio test. I'm going to go ahead and use this one just so I don't have to deal with extra negative exponents. So we want to compute the limit as, so we've got k now going to infinity. We'll have k plus 1 over e to the 2 times k plus 1 divided by k over e to the 2k. All the terms are positive, so I didn't need my absolute values in that case. We'll go ahead and flip the denominator. Let's go ahead and simplify that. So 2k plus 2 in that exponent times e to the 2k over k. Order your terms if you'd like. So we'll just have k plus 1 over k times e to the 2k over e to the 2k plus 2. And then if you want to simplify that, exponential terms will simplify nicely in ratios. So the 2k's, e to the 2k and e to the 2k will cancel, and we are just left with 2 powers of e in the denominator. And now when I compute the limit of this guy, polynomials will go to 1, and then the exponential term will dominate there. So the ratio is 1 over e squared. Which is less than 1. So e is about 2.7. Squared is going to be, some fraction less than 1. The series converges. Any questions on that guy? All right, so we've only got like 4 minutes, so let's go ahead and I'll end it there. Remember, so we've got